It's time. Welcome back, everyone. We finished off last class all of the course content for our course, so that was kind of exciting. Then we didn't have as much time as I thought getting into this final exam, but we're going to spend all of today, all of next class, going over this document here. We're currently on example 2, so we chipped away at it last class. We'll probably have plenty of time to complete this document in its entirety. So I'll also be taking possible questions from you as well that you might have today, as well as on Thursday's review. But that's pretty much it for the announcements today, kind of short. Quiz 12, or you know what, that's actually quiz number 13. We should probably fix that right now. Quiz 13 is going to be due tomorrow, so that's our final quiz for the semester. As far as everything else goes, the last day to work in my lab, turning quiz, will be May 7 on Thursday. I believe that's 11:59 p.m. for the official time. And if you haven't scheduled your final exam yet, please do so as soon as possible. Don't forget, it's going to be 2 pages of notes. A calculator will be required, and this document here will be the last page of the real final exam. But any questions whatsoever, folks, before we get started? Okay, well, if you'd like to start fresh at any point with this document here, you can go up to the very top of the Canvas course page, click on blank lecture notes, and that's the last file there. And I guess, by the way, while we're here, if anything is missing on Canvas, if a record lecture seems to be missing, maybe I just forgot to put it in the playlist. If there's a missing set of lecture notes, or if you're going through Canvas looking at, say, the solutions to Unit 4A and maybe a problem solution is missing, please let me know right away. It's easy to drop the ball somewhere here. There's lots of moving parts, lots of files going from to and fro getting uploaded, and I'll get it corrected as soon as possible. So just let me know if anything seems amiss at any point. But aside from that, we're going to jump back into this review here. We'll be calling out some hints about studying for the final exam, problems you should expect as we're going through the notes. But my idea with making these is, again, to try to give you a good preparation for what a real final exam is going to look like, to give you a nice representative set of problems. So we finalized the first problem here, just doing a unit analysis, making a conversion from kilometers into feet. You could expect some kind of problem along these lines where you'd be going to the very last page of the exam to look up information as needed, as we did here for kilo to get into a kilogram, and finding the conversion factor between meters and feet to start off the problem. So let's try out the next problem then. Problem number 2, I believe this still has us in chapter 2, probably the section or the unit B, extending unit analysis. We did a problem pretty similar to this, I believe, on our lecture notes. Similar problem on exam 1. By the way, reviewing your exams is a great way to study for the final exam. And so here's how this one goes. An island nation, Bahrain, hopefully pronounced that right, has a population of approximately 1.5 million people living in a land area of 300 square miles. We want to calculate the population density in people per square mile for Bahrain and round to the nearest person. It's kind of a tricky problem when you first read it, but when you really look at these instructions, the way the problem's being phrased, when it says people per square mile, the question, or I guess that's not a question, there's no question mark, the objective of the problem itself is telling us what the formula is. So we can write an equation that goes density is number of people. When it says per, we just think of that as a literal division bar, so we're dividing. Square mile, we can, it might not necessarily be in square miles. It could be in square meters, any kind of unit like that. So it's a good idea to maybe write the formula as per some amount of area. Square miles in our problem. So we go to the population size of Bahrain. If it's 1.5 million, but we want to round to the nearest person, here's where we have to be a little bit careful. We're not taking the area, 300 square miles, and dividing it into 1.5, we need to expand that out. If it's 1.5 million, another nice thought is this table is kind of helpful. Mega is just meaning million, really, for other kind of units, which means it's 10 power 6. So you could, in fact, go to a calculator, just write 1.5 times 10 power 6, and you get that number. So either way you visualize it, 1.5 million is going to be 500, there's the 500,000 part, 000 people, and this is per square miles. So there's our value. Now we just need to compute this. This looks like it's going to divide evenly, so the rounding wasn't super needed on the instructions. So 1500 or 15, yeah, 00000. Desmos does not put in commas, so you have to be a little bit more careful here. That looks about right, just double checking the zeros here. We have 5,000, so this tells us the density of Bothron is 5,000 people per square mile. So that's our rundown for that one. Any questions at all, folks, getting that first part done for the day? Okay, this is kind of a random geography problem. I don't know where on the map this is. I probably should know that if I wrote the question. But, we don't need to necessarily be an expert on geography to get the density, nor to do the follow-up question. Follow-up question is more relatable. It says, if that's the density, 5,000 people per square mile, how many times greater is the population density of this island nation compared to the city of Pocatello? And here's a figure I researched. It approximately has 1,688 people per square mile. So here, this one is a kind of a tricky question, but we've seen these kind of things before, even in the last unit. When it's asking how many times greater, we resolve the question by dividing again. We take the thing that comes first, population density of Bothron, which we just calculated, 5,000 per people per square mile. Because that came first, it's going to be the numerator in our fraction. So we'll throw in 5,000 people per square mile. So that's the numerator, or top is a good way to say that in the notes. We're comparing that to the other thing, the population density of Pocatello, which was given to be this value. This is the quantity that came second in our comparison. So this will be the denominator. So throw down below 1,688 people per square mile. And one comment on when I go to grade the exams, I'm not going to be picky on units. So if you left off people per square mile here, I'm not going to dock you for that. But sometimes it is important to track these through to know if we're computing just right. And here, all that would happen is it just cancels out, which is where our expectation is. If it didn't cancel, we've made a mistake somewhere. How many times greater is going to be a unitless result. This one gets rounded to the nearest whole number. So here's what we'll get. 5,000 divided by 1,688. To the nearest whole number, this one is going to round up to 3. So, that satisfies the whole entire problem. Just for the sake of notes, to see what we calculated, to see if it feels reasonable. If you get 3, this is saying population density of Bothron is 3 times, and that is an approximation, I'll put it here just to emphasize, the density of Pocatello. So when you walk around, drive around Pocatello, just imagine 3 times as much people and you get a feel for what it's like to be in this island nation. Well, any last questions at all, folks, getting through this one? Okay, on the real final exam, it's important to be economical with your time. Strategy is to just demonstrate your knowledge on as many problems as possible, getting them to as complete as possible. So I'd say once you know you've answered the question, it's okay to just leave the answer right there in that form where I wrote the 3. You might want to say this, maybe just in your own mind, in the back of your mind, to convince yourself that the problem is, or your numbers are reasonable, but you don't have to write that down on paper. It's not required. So anything in orange, just like we've been doing with the lecture notes, just an additional comment for the sake of if you come back here to review this information. So let's go to the next question. Seems like we're changing gears a little bit on this one. This is a good one where you probably would want to cite your formula sheet that you brought to the exam. We have done a question like this one. I believe this one was on exam 2, but they're tricky because there's 2 quantities. There's a 2023 figure we're going to look into compared to a 1958 figure. We want absolute change or relative change, and the organization is critical. So let's go to the notes. Here's something I would suggest for your pages of notes. I believe this is going to be in unit 3, probably B. So let's find a problem that looks about like that. Actually, I think it was 3A. It's been a while already for some of these problems. We've been through a lot. So here we've got some kind of formula for sure. I don't know how to make that go away. Maybe I can just reopen it. Well, let's ignore that little tag there. Shouldn't have used Microsoft Edge. I knew that was a bad call, but let's stick with it. Okay, here's the formula I was trying to find. So this is a nice set of 2 formulas all together. Just debating on where to put it. That should do the job. And so this is a good set of formulas to cite as you're doing this particular problem. So we want absolute change and then relative change. Let's read through the context fully. Global average atmospheric carbon dioxide, CO2 concentration, increased from approximately 315 parts per million in 1958 to about 420 parts per million in the year 2023. So we're calculating first absolute change. Absolute change says we're just looking into the difference of the new value minus the reference value. The new value is going to be the most current data, 420 parts per million 2023. Reference value is the historical data, 315 in 1958. So we can pretty rapidly answer this question by saying absolute. I'll just abbreviate to ABS. Change equals, take the new value, 420, parts per million minus the reference value, 315, parts per million. That looks 105 parts per million altogether. So that's how much global atmospheric CO2 concentration is increased approximately. These are both approximate values from 1953 to 2023. That's all, folks, with the absolute change. Okay, and I'll be trying to do this all along as we're doing our review. Any formula that I would say is a good idea to include, I'll screenshot it like this. Unless, say it's the first example, if it's on the formula sheet that's on the real final exam, last page, you definitely don't need to include that. Last thing is we're being asked to is find the relative change. Here, the order is now very, very critical. If you mixed up the order here, you're going to get a negative sign, and you'll get most of the credit through partial credit grading. But if we mix up order here, our percent is actually way off. That would lose us even more points than in part A, because the reference value absolutely has to be in the denominator. we're looking at how much it increased in terms of a percentage as opposed to the absolute change in 105 parts per million. So relative change, I'll abbreviate to REL for relative, change equals, nice little shortcut is, notice the parallelism in the formulas. If you calculate absolute change, that is what goes into the numerator for relative change. So take that same number, 105, parts per million. Critical thing is whatever you consider to be the reference value must be the denominator. So if you swap these, but the thing that was here, you did put in the denominator, you're at least being consistent, and you probably wouldn't lose any credit at all on part B, just a little bit on part A. So I do look in how you solved a prior part. I'm not going to take off extra points if you did it correctly, you did in part A. So the major idea is the thing that came second is the denominator, 315 parts per million. It's a percentage, so go times 100%. Also indicated in the formula. Units are just gone, so now it's back to being a calculator problem. It would be 105 over 315. Either move your decimal 2 spots to the right or just go times 100 is an easier way to visualize and be accurate. Rounding to the nearest tenth, so it'll be 3%. It's a repeating decimal, so if you said 33.3 bar, that'd be completely fine with me as well. But here's what we would do if we were following the instructions to the letter. Well, that means it's been about a 33.3% increase from the 1958 value to currently. So by a third, that's a pretty gigantic amount. Any questions so far, folks, with the conclusions here? Okay, well, let's go on next to the next problem. It feels redundant saying it like that. Maybe hide that table for the moment. I think we're still in chapter 3 when we're looking into this one. We're looking at practicing with scientific notation, rules for exponents, as well as significant digits being the major parts of this problem. So for full credit, we have to pay attention to how we're going to round. We want to answer to something with 3 significant digits in particular. Likewise, 5 significant digits on that one. I did something pretty similar on the real final exam. It's just 2 parts. One is going to be just a basic thing. The other one's going to have a little bit of context. But if we follow the operations indicated, we'll be on the right track. This one just says to multiply. And there's some really good strategies here. First, multiply the numeric part. So let's go into the calculator. We are taking 4.105 times 2.35. Now this problem kind of works out nice for us. We want to answer in scientific notation. So if that was larger than 10, we would have an extra step. We've done a couple problems like that in the notes before. So if, for example, it was, here, if we had a 21.96715, what we would need to do is rewrite it as a 2.1 and put a power of 10 to the right of it. This one came out a little bit nicer. We're going to just stick with that there. So take to 3 significant digits, 9.65 rounding up. Next thing we're going to do is combine those two together. Let me first write it in as 10 power 6 times 10 power -4. Where all that happens with the exponential notation is that the powers add up. So this would result in 9.65 times 10 to the power 2. I have second opinions on how this should be color-coded. 3 significant digits are those 3 digits we see there in blue. And this is just the scientific notation part. Well, any questions at all, folks, getting through this one? Okay, again, nothing too serious. This is something you can get a lot of partial credit on by just getting the three significant digits just right. That's the major thrust of this problem. You do have to get the scientific notation dead on, so you might lose a point if this isn't written as an appropriate scientific notation. If it was a 96.5, you might lose a point there, but the significant digits is the major part of the credit for this one. And part B, really it's the same kind of thing, except for being told to, on this one, instead of multiply, we're dividing. It has some interesting context for people curious about this kind of stuff. Solar flares cause all sorts of mass hysteria events for computer systems, for example. It says an active solar flare releases a total calculated energy of 4.2055 times 10 to the power 25 joules. Massive amount of energy, more than what we saw for our earthquakes, I believe. I'd have to double check the order of magnitudes. We also know something else about these energies. One proton, one piece of light in a certain sense, to say it in a way that might make a physicist cringe a little bit, one proton emitted in a solar flare emits this average amount of energy, 1.5512 times 10 to the power negative 16, minuscule amount in joules. So if the total energy is that many joules, but one proton has this much energy in joules, we can divide total energy, this value, by the photon energy, the thing that came second, to estimate the number of photons released on a solar flare. Well, one that releases that amount of energy. There's variation in how much energy gets released too, probably a huge amount of variation. So all we're doing is taking this number, starting out 4.2055 times 10 to the power 25, dividing it by the second number, 1.5512, multiply this one by 10 to the power negative 16, and get a value out. So again, even if the context doesn't seem that interesting, this is really just the punchline to this. Really, the skill that we're testing here is similar to our chapter 5 on statistics, of extracting information with context to get down to the main computation, analyzing context. Then we do it in the same kind of way. We can just go to the calculator, divide this integer or decimal number parts, and then work out the scientific notation portion. So now let's do this in stages. Take 4.2055, divide by 1.5512. This one is to 5 significant digits. So that's a 2.7111, no rounding. Then we're going to work out the scientific notation part. Let's maybe do that as scratch work on the margin to the right. If you have 10 power 25, divide by 10 to the power of negative 16, as opposed to this situation where we just took 6 plus a negative 4, added them together, effectively subtracting them when we added the negative. This one goes different. We're going to subtract the exponents. That means we're taking 25 minus negative 16, and there's double negation. So that one is a little bit trickier. Not a bad idea to take an extra step. Write it as 10 power 25. Rewrite this base 10 by putting it up into the numerator. Our exponent law, way back in chapter 3, I believe, tells us that becomes a positive 16. And now it's a cleaner operation. We're not worried about the double negation. We can add these together to get 10 to the power 41. So this is the by-hand approach. Sometimes it's effective. But I also want to emphasize your exam is open calculator. To get this computed right, either method is going to be fine with me. So if you did it this way instead, go 10 power 25, divide by 10 power negative 16, you'll get the same thing. You can ignore the 1 times and just bring in 10 power 41. I think it's convenient to do it this way because sometimes that is tricky to put in a calculator with exponents, quantities being divided. But in the end of the day, this just turns into times 10 to the power 41. Let's put the units on this one because it had context. Photons. So that is a gigantic order of magnitude, 10 to the power 41. It's kind of inconceivable to say just how big that number is, but that's because photons are very minute particles, and a solar flare releases gargantuan amounts of energy. Well, any questions at all, folks? Getting through the pretty much the significant digits side of the exam? Okay, now I think we saw the CPI table, so we spent a lot of time talking about the consumer price index, indexing is general. The federal minimum wage table was also pretty interesting. It was in the homework. We spent some time on it. I felt to keep the exam contained and not to throw in so many tables so it didn't feel like we're printing out lots of pages, the testing center would be upset. We're mostly going to focus on this CPI table that we see here. So let me hide problem 6. And you might have noticed a lot of our problems references the year 2025. That's not a guarantee. It could talk about the year 2020, year 2000, anything along those lines. That just happens to be one of the more interesting years, so it did get asked a lot, but no guarantee. This one's going back all the way to 1983, almost to the start of the table. 1983 was a very important year for a lot of people. In home entertainment, it corresponded to the release of the Nintendo Entertainment System, called the NES, one of the more legendary consoles. So back in the early 80s, a family had to spend, and this is a pretty rough estimate, about $300 to purchase an NES, which I think probably costs about $200, as well as an extra game, which was very expensive games, and a controller. So again, that figure is maybe not totally accurate. So let's just think of that as a loose estimate. Maybe they bought a couple games or something like that, or several controllers. So now the question is, if this family spent $300 in 1983 money, how much did they have to spend to get the same equivalent economic value for something entertainment-wise, PlayStation 5 or something like that, in the year 2025? How much would they need to spend? So this is a good one that has a lot of interesting formulas you could write down. I think a good formula would look along these lines. Let's pick out one specifically. Looks like I'm already on the consumer price index. Now, this is basically the formula, but it's more of like a schematic where there's particular years already drawn in. So you could work this out as a formula if you like. Just put in anything you want in for these years. Let's go that route. Let's take this exactly as we wrote it. We can wipe out a couple elements here, make it our own formula. So instead of $2025, well, it is $2025 for our problem, but you can put here a couple blanks and just write in here year X, whatever it is. That'll be year X here as well. And then year Y would go here. Year Y would go here. I think that's about how the formula stated a lot of, how the book stated a lot of their formulas in this unit. So the idea is this could be either value or a past value. But if we're being told how much would the family need to spend in 2025 dollars, the question always goes on the left-hand side. So find out what the question is in the problem. And that gets the formula started. Beyond that, you're going to use a reference year, the 1983 amount. So for the 1983, we're using this amount. And then the ordering beyond that is whatever the question is goes into the numerator. the reference amount in the other year is going to go into the denominator. So putting that all together, we can now say for our particular problem, amount needed in $2025. I believe you also did this one as a quiz, so that'd be a good one to look into as a refresher, is going to be equal to, take the amount in year Y, that's 1983 for us, which is $300. So let's write this in as $300 in 19. I wrote in twice. Let me try that again. In $1983, multiply that against. We take our CPI values. So we want the CPI. And we often wrote this as a subscript. So CPI for 2025, divide by the CPI for 1983. Or once again, when I say CPI, I just mean the Consumer Price Index. Same table that is used to determine inflation by the USA government. Now, finally, we can plug in our values, get it computed. This stays exactly where it is, $300. We multiply it against the fraction. Now we're actually doing the table lookup, CPI in 2025. That was a gigantic jump, it looked like, 321.9. Consumer Price Index in 1983, that was a nice year. I believe this is part of the reference years, 1982 to 1984, which gives us index 100. So 1983, it was in fact below 100, 99.6. So this is how much money you're going to need to shell out to get the same equivalent entertainment value in terms of $300 spent in 1983. And you can judge if that seems reasonable. I haven't bought a console in some time, so I'm not completely sure. So back to this table, or calculator rather, take 300 times the fraction, 321.9, divided by 99.6, and we get, this didn't say what to round to, but you can always assume on this exam, if it's money, the nearest cent is the big assumption, $969.58. So to buy a brand new next generation PlayStation, Xbox, or Wii of some kind, or I guess that's called something else these days, that would be what we're saying you have to spend in 2025 dollars. As far as I know, again, I'm no expert on that these days, but that seems about right, shelling out $1,000. Any questions at all, folks, getting through this one? Okay, again, that's a lot of money, but $300 in 1983 was a lot of money back then. This doesn't seem like a lot of money now because, well, inflation's taken its toll over the decades. So let's go on to the next problem then. Again, this is another nice formula that you're going to want to have ready to go on your sheet of notes for the exam. And maybe just another hint about preparing for any exam. As far as what goes on your 2-page of notes, your formulas, your definitions, I have no restrictions whatsoever. So if you want to model a problem, maybe something that we did here as part of what goes on your notes, it takes a little bit more space. It's up to you. That's a judgment call you can make, and I'm not opposed to that either. I would say that's a fine way to study for the exam and to internalize this information and to really learn it, is to write down model problems. So you have a lot of strategies to get prepared for the final exam. And this set of problems are going to be fully very representative to the real problems that you're doing as well. So going on to the next problem, number 6. Here's where it becomes really heavy with the calculator side. We're now moving off to the next chapter on managing money. So we have formulas that are provided for us on this. In fact, the formula sheet as well. has these ready to go, so you don't necessarily have to duplicate these as formulas on your pages of notes. So here's our first scenario we're going to take a look into. It says, suppose you sell a fully restored classic 1967 muscle car at a vintage auto auction for $23,000. Context is minimal, didn't say what kind of car, unfortunately. Instead of spending the money, you decide to invest the entire amount for your retirement. You place the funds into a high yield investment account that earns an average APR of 4.05%. Kind of highish yield. That's a little bit moderate, but if it averages 4.05% for the life of this investment, then maybe it's not too bad. It'll be compounded weekly, and we want to know what will the value of this account be in 15 years to the nearest cent. So here, if you see questions like these, financial questions, this is going to be finding the future value of account. Go to your formula sheet. And this is the structure we're going to use. Let's throw this in. All right, here in the notes, just as a reminder, from included formula sheet. So we need to find several values. We want to know what the principal is. As far as these problems go, I'm going to grade with partial credit, just like we did on quizzes and exams. So this alone is considered a great deal of partial credit on its own. This problem is also about breaking information out of context, like we did on a prior problem, like we'll do with some of the other problems. There is a good amount going on here because there's several kinds of numbers we have to grab. The principal amount invested is the $23,000. Next thing we need to spot is the APR. It says the APR is 4.05%. But here's where we're needing to be really careful. There is only one formula in the entire course, well, two, doubling time and half-life, where you don't do a decimal shift on this. But for every other formula, especially financial ones, you have to take the percentage and now shift it over to a decimal. So APR on this one is 0.0405. And the check on this is pretty fast. If you just feel you're unsure, it's easy to kind of second guess yourself on an exam. Take anything as a percentage, 4.05, divide it by 100, and that's the equivalent decimal value. Or go backwards, if you have the decimal value, 0.0405, multiply it by 100 to get the percentage, and it gives us this. So really all we're doing is we're moving the decimal spot 2 places to the right as a percent, 2 places to the left as a decimal when using in the formulas. But the calculator, again, it's a good way to just be numerically sure you're right on the right track, that we didn't get tripped up with any of the zeros, any weird APR. So we almost have everything. The next thing we need is, let's see here, running out of colors, but when it said compounded weekly, that's the number of compoundings, n. So here, n would have to be equal to 52 altogether. I think it's more common that we saw compounded annually, n is 1, or compounded monthly, n is 12. So if it's anything like quarterly, 4, semi-annually, twice, or even compounded weekly, I probably would tell you n is 52, n is 2, 4, so on. So this one is kind of an unusual one. I don't think we did a lot of weeklies whatsoever. Finally, the last thing we need is the term of the investment. This is for retirement. So I guess this person is planning to retire soon in 15 years. So that's this value. Y equals 15 years. Ran out of colors, but we could still kind of underline something. So now all we have to do is put it all together. Again, doing this amount of analysis, telling me what is what in the formulas, I consider this to be a decent amount of partial credit. Any comments at the moment? Spotting the values? Okay, then I'm going to grade these with partial credit, same exact way as we did on exam 2 and on quizzes. If you give me, hang on, I think I grabbed the wrong formula. It looked okay for the moment until I'm about to calculate and it says payment. So, I guess this is a good moment to have occur when you have lots of formulas, whether it's on your formula sheet or the formulas that are included. Watch out for a mistake like this one. This one's kind of a silly mistake. This one goes to the next question. Let's throw it on the next question. This one's asking for the monthly credit card payment. So that's what PMT is all about, the payment. So let me try again on this one. Let me go back to the formula sheet. That's what we want, the compound interest formula. So if you noticed this and you were kind of screaming at your computer, that doesn't look right. Good on you. I agree with you totally at this point. Let's grab that, plug it in. Color coding did not quite survive, so let's fix that as well. Okay, so another try at this. The principal goes here. APR is in this location. Number of compoundings goes in these two spots. And the years goes in here for Y. So now we're ready to go. The amount in this account in 15 years is going to be $23,000 principal amount times, let me fix that, times 1 plus the APR as a decimal, 0.0405. We divide by the number of compoundings. Weekly would be 52 altogether. Raise it to the power of 52 times 15. And if you have a calculator handy nearby, then practice this along with me and let me know if you're having any issues with it. Like we've done before, I'm very happy to spend some time just looking into the calculator input-output side of this problem. But here it all is. And just like on exam 2, when we got through a question like this one, if I see this work on paper, I consider that to be a major amount of partial credit. If it's a 5-point problem and we miscalculate, maybe we just had a mistake in the calculator, exam nerves can make that happen easily. You might lose maybe a point, even a half a point, depending on the problem. So this is really major insurance against any kind of small, easy to make mistakes. If you're feeling extremely confident, you give me the right value, but no prior work, I will get full credit on that, but that's a risky maneuver on a final exam. So let's put this in. Let me know if you're getting any different issues. 23,000. 1 plus 0.045, excuse me, 0.0405 divided by 52. Now for this part right here, if you're computing this in stages, you should keep lots of digits on this, like something along the lines of maybe 5 or 7 decimal places is good call. Especially if you're doing this as a MyLab problem, probably keep all the digits to be as accurate as possible. Because I mean, it is money after all. We want to get this right to the nearest cent. But I'm not going to be too picky. If you're pretty close, I know you rounded to say 1.0007 or 77, our values are going to be a little bit off, but that's enough numerical evidence for me that maybe you just rounded a little bit funny, but you're on the right track. Let's go 23,000, bring that back, raise it to the power of. It's not a bad idea to compute that first. It's easier to put in the calculator if you have the number 52 times 15 ready to go, 780. So let's do it in that way, just to emphasize. That gives us a little bit more accuracy in the calculator as well, pre-computing the exponent. And there's our value. 15 years have gone by. It wasn't super high, but that's respectable as a APR, unfortunately, barely beating inflation. $42,214.25. I think I'm way too tired to remember all those digits. 21425. Okay, let me double check. All right, looks like we've got it. Well, that's one big financial formula down. The next one, we were looking at the formula already, takes a little bit more, but if you can get through this one, you can absolutely get through the next one as well. Any questions or comments getting that number? Okay, let's try this out all over again then. Problem 7. I think we would probably want that on a new page on its own. Same kind of stuff, but different scenario. Now we're using the loan payment formula for installment loans. So here, this is another exam provided formula. I believe this is the last one. The context says, suppose an unexpected mechanical failure required an emergency car repair to replace a blown transmission. Sometimes that's going to just be itch for the car, depending on the model. To cover the costs, the owner had to use a high interest credit card, unfortunately, with a fixed APR of 27.99%. So thinking in terms of what we did before, we have that value, APR, converted to a decimal is going to be 0.2799. Those 99s are kind of annoying, but that's often what credit card companies do to make their rate look nice. Doesn't quite make it to 28%, right? The total balance on this card has now reached $6,245.50. That's a heavy balance for a credit card, but you know, these things happen. So if you ever find yourself in that position, I've been there as well. This is kind of a nice formula to think about how to get out of there, how to dig out of the hole. So that's the principal part right there. It only goes into one spot. Principal equals 6,245. And let's not forget about the 50 cents because the credit card company won't. Compound interest occurs on that as well. So we've got a couple elements. We have APR, which goes into 2 locations. We're going to figure out the year, reading through the context. They are determined to get out of this debt and plan to pay off the card completely over a 5-year period. And that's duplicated down here, paid over 5 years. So this means time in years is 5. So we need that figure as well. That goes into that spot right here. Assume they lock the card away. I think you can actually lock your card so no purchases can be made to kind of help out. So absolutely no purchases are made during this 5-year period. So for this formula, we did make a comment that it's always implied to make this a realistic problem that n is 12 because we're expecting monthly payments. We never threw it into the formula because it's meant to be a flexible kind of equation. Some say car loan companies where you buy here, pay here, they make you pay twice a month, I learned. So that would have been a 24. So this is as realistic as possible, leaving it as an n. But here's the hint on what n should be. It's a monthly credit card payment. So it will say verbatim somewhere in the context, usually in part A, n is 12, but it's a safe assumption on the exam for this specific formula. So that's our dissection of the context. The values that we have down, now we just have to run through this formula. I remember this one was the extra tricky one. So it's not a bad idea to divide and conquer, compute the numerator first, compute the denominator first, keep all the digits in your calculator for accuracy, and then just divide the two. I'll put it all at once in Desmos and let me know if you're getting anything different when we compare values. So first, let's write it down on paper. Payment equals, again, this is for insurance on your problem, massive partial credit for getting this, 6,245.50 is going to multiply. We're in the numerator here, so make the next substitutions. I forgot to highlight the n values. Put in 0.2799 over 12. Divide the entire quantity by, throw in a bracket, sorry, because we would need that in a calculator. 1 minus 1 plus APR again, 0.2799, divide by 12 again. And this is going to be to the power of, let's use this strategy of taking that whole thing, negative n times y, and just pre-compute this. It's a good idea for an already long thing you're going to put in your calculator. And oh, don't forget that the bracket should close out here. That should have been a parenthesis, not a bracket that I drew on that spot. So negative n times y is going to be negative 12 times 5 for a negative 60 altogether. So negative 60 goes there. Now we're shoving it into the calculator at this stage. The payment to pay down this balance at a heavy rate, the prime lending rate has gone down, so your credit card rates are not always this high any longer. But this was realistic about 6 months ago. Here's what it's going to come out to for a payment on that. So 6245.2799 divided by 12. So again, you can write that down on paper as your numerator. I'll put this in one shot and now go bracket 1 minus 1 plus 0.2799. Don't forget that open parenthesis there. Forgot to say it. Divide by 12, right? Raised to the power of. It's got to be specifically a negative. In your calculators, often that's a special sign you have to use on the very bottom, very right of your calculator, not the subtraction sign. So power negative 60 gives us this as the payment. And 5 years is a long time to pay this off. So the amount seems kind of reasonable. So if the budget was tight, they might have just been forced to make that decision, paid in 5 years. $194.41. And honestly, that's what you would round to. But even if this was a 4 in that place, it's usually a good call to round up to the next near cent anyways, just for the sake of making sure it's really, truly 100% paid in 5 years. Usually we wouldn't round down, but do anything that seems reasonable on your rounding. I'd say rounding up always is a good call, but if you round as normal, that's fine as well. $194.41. So that's the payments altogether. Amy says, do we have to leave off the 50 on the P amount? Let me double check. Oh yeah, that we should not have left out. Thanks for spotting that. So we should absolutely include that. That was my mistake there. Good eye. So $62.45. And I think I remember making that comment. Don't forget the 50 cents because the credit card company will not. So let's revise this. Let's leave this on paper. That's kind of interesting now that we spotted that error. Fix it by putting in the true principal, 50 cents. Every cent does matter. And notice that rounds up to 42 cents. Going by prior comments, putting in 43 cents would make sense here. That would be the sensible thing to do if you're doing this with your own personal finances. But I'll round it the normal way, make this a 42 cents. Thanks again for spotting that, Amy. So 42 cents is exactly what we should have. And because this is dealing with interest that's accruing, it's going to make more than a difference of 1 cent per month because there's interest accruing on that missed cent, that missed 50 cents as well, really. So getting that down right will make a surprising difference at the very end when we're looking into part B, part C, and so on. Well, any questions or comments at all, folks? Getting that number? Any calculator or different computational techniques or strategies you want to take a look into? Okay, well, let's go off now and do the follow-up questions. Every time we did a question like this of payments, we always had 2 more questions to look into. And these are reasonable questions to take a look at because we should never be concerned just by the payment. We want to determine how much is it really going to cost to pay down that principal if the interest rate never ever gets adjusted over the 5-year period. So this might make you change your mind. Maybe we'll try to go for 4 years instead if we're doing this in a realistic scenario. So we're going to say here, total amount paid over 5 years is going to be equal to, we take the payment, but recall this is per month, so 194.42 per month. Multiply that by, we need to know this value in terms of years, so we multiply by 12 months per the year. Then we're going to multiply this, shouldn't be a fraction, let me backtrack on that step. Multiply that by 5 years. But really, if you did this as one big shortcut, you all might have noticed that it really just boils down to take 5 times the number of months in the year, 12. In other words, you're just using that number without the negative sign. So just multiply that by 60. This is the logic, the unit analysis that tells us we're actually in the right track to multiply in that particular way. Time units completely annihilate, and we're just getting a unit in dollars. So here's what it looks like. Putting it into the calculator verbatim, 194.42 times 12 times 5 says we're spending $11,665.20. And I feel like I mixed up a digit. 11,665, 20 cents, not 12. In accounting, every cent matters, so let's put that in right. 20 cents. So that's a lot spent. It is an approximate amount because remember, we did round up, but that was a sensible way to round. We're spending a lot, right? That's almost double this figure here. So now that we have the total amount spent, the next thing that's interesting for us to determine, just to get a better context of how big is that number, is what percent paid was towards the principal, 6,245.50 cents. Now, what percent went to interest? So we're going back to these two things. Usually this is where the problem kind of calms down a little bit more. Part B, part C, they're not too bad. And even if you make a mistake in part A, just use whatever number you have right here. If you're having trouble putting it together, guess even. I'll give partial credit for an educated guess. And whatever number you have here, if you do these steps right, you get full credit. I'm not going to take off points just because you have the right number. I'm concerned about the logic on that step. Do these steps exactly right with your prior part B, part A numbers, you will get full credit here even if you made a mistake in part A. So here's the conclusion to this problem finally. For principal, when it says what percent is paid towards the principal, the what percent paid is referring to the total paid. So that's always going to be the denominator for this step. Put in 11,665.20 cents. Towards principal, that's the numerator, the same amount that started this off. 6,245.50. 0.50 is a better way to say that. It's a percentage, so we'll multiply that by 100. Throw in the percent symbol to remind us it's now a percentage. The units are money, same unit numerator denominator, so they cancel. And here's what we get as a percentage. 6245.50, 11,665.20. It's not quite a percentage yet, but it already looks bad. It's close to, well, it's more than a half, times 100. And, I forgot to say what to round on this. I try to be extra careful about the instructions on rounding on an exam, but I'm not going to be too picky. If you round something incorrectly, but you're on the right track, you'll still get full credit. And if I, for some reason, forgot to say what to round to, then anything goes. Round to just what makes sense, the most sense to you. I would say 1 decimal point is pretty common for this type of analysis. So let's call this 53.5%. So that's rough. It's even worse if this is below 50%. But what this is saying is over the 5-year period, paying 194 and 42 cents to pay down this car to zero, you're barely spending more than half of your payments on the original balance, 6,000 to fix the transmission from the original context. So I think the first time we did this, someone said that that's a kind of a disgusting figure. That's kind of rough when you look at these values. And I would agree, this interest rate is really brutal when you take into account 5 years, making the payment low, punishes us egregiously on barely sending as much as we'd like to the underlying principal. But sometimes we're just cornered into those size of payments, and we just have to live with that. But any questions at all, folks, on the first part here? Okay, the second part is really fast once you get this down. All you have to do to say for interest portion, here we're essentially using the complement rule. There are two parts that make up a whole of 100%. Money either went to principal or it went to interest. So if you know the principal side, that means you can take 100% minus the principal part, 53.5, and this will give you the part that's in interest. So this becomes 100 minus 53.5 for 46.5%. Pretty close to half of the payment just went to the credit card company. Well, at least the transmission's working. Going back to the original context of what they charged on this car, this is just what life does to you. But it's kind of interesting. If you do have a credit card balance, you can do these kind of scenarios at any time. That would be a great way to kind of practice for the exam. Run this on your own finances. If you don't have a credit card balance, good on you. That's awesome. Pretend like you have one. Suppose emergency happened, make up a ridiculous APR. And this is kind of a fun way to analyze what could happen to your finances. Any last questions or thoughts at all, folks, getting through this one? Okay, well, we're nearly out of time. I'm kind of glad that Zoom is working out a little bit better today. And just by the way, I did go to the IT department here on campus. I opened a ticket about Zoom instability. And what I learned is that this is campus-wide. This is a Zoom problem. Zoom pushed out a new update. It's kind of making instability occur for everybody, whether you're part of ISU or if you're working for some other corporation. Everybody is having trouble with Zoom. Zoom is aware of the issue and they're trying to work on it. So I just hope that the rest of the time here on a Thursday's class, we don't get another one of those weird crash outs, laggy experiences. Well, we're nearly out of time. I think problem 8 is pretty important. This one was on exam 3. I'm going to ask another question like this one on the final exam, and it's a tricky question, but the reason I want to come back to it is, as far as the chapter 5 on statistics goes, this is one of the major fundamental ideas about statistics. The dichotomy of the population versus sample, parameter versus statistic. This is going to be our redo on the final exam. And even people who take a statistical class, even a follow-up statistical class, this is tricky. So this is one of those skills that just has to be practiced to get down pat. So if you feel like you had a rough time on the first round on exam 3, we'll try it again. When we review this problem, we'll have another one, different context that we'll take a look into on the final exam. I'll grade it on partial credit. So any elements you get right on any one of these parts, you will get credit for. But again, I think this one takes time. It's tricky. So let's see what else we have going on in about 5 minutes. We have another one where we're going to look into a scatter plot. We're going to have a table like this one where we're looking into percent change. And finally, looks like 2 more formula kind of problems we're going to look at. This is the we covered that we finalized on earthquakes. This was growth and decay. So these are the 2 problems from Unit 8. Now, honestly, they all look like they're pretty big size. I don't want to rush through any one of these. I think we're in really good position for finishing the final exam, however, when we come back on Thursday's class. without having to rush through any of these important problems. So I think I'll turn it over to questions from you all, and then we might end a couple of minutes early today's class so we can take our time, not try to rush through anything. Any last questions or comments whatsoever, folks, with where we've ended at today? Okay, well, we'll finalize the last of these problems when we come back next class. This exam happens to be 12 questions long. I think the real exam is about the same, about 12 questions. There's one extra credit question that we've mentioned before. That extra credit question is to get this unit down pat, particularly the problem with the logistic growth rate specifically, that one is going to be the extra credit question on the real exam. The extra credit is pretty substantial. Your final exam score can't exceed 100%. So if you decide to push forward in that section, get it done in the MyLab homework, study the problems that we did here, you can get some extra credit, extra protection about making any other silly mistake anywhere else on the exam through that concept. But we'll return back a little bit more fresh, ready to hit probably the trickier exam on the exam, problem number 8, on Thursday's class. Have a great night, folks. We'll be back to it next time.